Hello everybody, welcome to the first part of my talk. I am Ivo Slegers, I'm a PhD student from the University of Bonn, and I will talk about the energy functional of Hitchin representations. Let's begin with an overview of the coming two talks. The first talk will consist of two sections. In this I will introduce the energy functional, give the necessary definitions and notations, and then in the second section I will discuss why this energy functional is of interest. This is something that I think is not immediately clear from the definition, so I will spend some time explaining why it's interesting to look at. Then in the second part, the second talk, I will discuss some results regarding the energy functional that I've proven. Let's begin with the first section, defining what the energy functional is. For that we will need three ingredients, namely we need to define what the Teichmüller space is, the Dirichlet energy functional, and equivariant harmonic maps. Let's begin with Teichmüller space. Throughout this talk we let S be a closed and oriented surface of genus at least 2. Then its Teichmüller space is the set of all complex structures on S considered up to isotopy. More precisely, we consider a complex structure on S to be an automorphism of its tangent bundle that squares to minus the identity. Two such complex structures are considered equivalent if there exists a diffeomorphism of the surface that's isotopic to the identity, such that one complex structure is pulled back to the other. There's a lot that can be said about Teichmüller space. We won't need a lot of information in this talk. Let me mention that topologically Teichmüller space is rather trivial. It's homeomorphic to R to the power 6g minus 6, where G is the genus of the surface, and it can be given a natural complex structure. So throughout this talk we will consider Teichmüller space to be a complex manifold. Our second ingredient is the Dirichlet energy. For this we fix a complex structure on the surface, making it into a closed Riemann surface, and we let N be some Riemannian manifold. Then, if F is some smooth map from S to N, then its Dirichlet energy is defined by the following expression here. Let me explain a little bit what's going on here. We consider the derivative of the smooth map as a one form on the surface that takes values in the pullback of the tangent bundle of our target. This one form can be composed with the complex structure because the complex structure is an automorphism of the tangent bundle of S. We obtain a second one form which we denote by JDF. These two one forms we wedge together to obtain a two form, and here the part of the one form that lives in the pullback of the tangent bundle we pair together using the bilinear form that's provided by the Riemannian metric on the target. This two form is then a two form on a compact surface, so can be integrated to obtain a number, and that number is the Dirichlet energy. I've put this expression for the Dirichlet energy on the slides to really emphasize that it depends very much on the choice of complex structure on your surface. We can also give a perhaps a little bit more intuitive form for the Dirichlet energy if we consider complex coordinates. So we let Z be some complex coordinates for our Riemann surface, and then in these coordinates the integrand can be given by this expression here. And in this expression perhaps the role of the metric on the target is a little bit more clear. And you should think of the Dirichlet energy of giving a measure of how much a map F stretches. How much you have to stretch a Riemann surface in order to map it into N along the map F. Well, if we have defined the Dirichlet energy, we can now define what it means for a map to be harmonic. A map from S into N is called harmonic if it is a critical point of the energy functional. This means that whenever you have a deformation of a smooth deformation of your map, by which I mean a smooth family of maps indexed by T, which at t equal to 0 are equal to f, then I want that the Dirichlet energy, which is now a function of t, is a critical point at t equals to 0. And this condition needs to hold for any such deformation. If this is the case, f is called a harmonic map. Of course, in this definition we require the domain manifold to be compact, because we look at this integral of the Dirichlet energy functional. However, if the domain is not compact, we can still define maps to be harmonic. What we then do is we simply require f to satisfy this criticality condition locally. Let's go on to the third ingredient. Once you have established what harmonic maps are, an important question is always whether we have some existence result regarding these maps. And the existence result that will be central to our discussion is a result of Corlett. So let's discuss this theorem. We consider the fundamental group of our surface and denote this by gamma, and we let ρ be some representation of gamma into G, which is a semi-simple Lie group without compact factors. Then Corlett proved the following theorem, that for every complex structure on our surface, there exists an energy minimizing harmonic map from the universal cover of our surface, equipped with this complex structure, into the symmetric space that's associated to the Lie group G. And this map is equivariant for the representation. And let me put on the slide what it means for map to be equivariant. It means that it intertwines the action of the fundamental group on the universal cover with the induced action on the symmetric space that's induced by the choice of representation. There are two more things to note about this theorem. First of all, I've put the condition here that ρ is a reductive representation, which is some condition on the representation that you can put on the representation. And this is a necessary condition. However, all representations we will encounter throughout this talk will automatically be reductive. So I'm going to sweep this condition completely under the rug throughout this talk. But still I wanted to put it on the slide in order to make sure that I did not state a wrong theorem. And then there's also the point of how unique these harmonic maps are. They are essentially unique, which means that two equivariant harmonic maps for the same representation can only differ by composition with an isometry of the symmetric space. So any such equivariant harmonic maps are the same up to a translation. In the next slide, I want to talk about the Dirichlet energy of these equivariant harmonic maps, but the domain manifold is not compact, so we cannot immediately use the same definition we saw before. Nevertheless, we can assign to each equivariant harmonic map a number that's the Dirichlet energy. Rather than integrating over the whole manifold, we simply integrate only over a fundamental domain of the surface in its universal cover. And in this way we can still assign a finite number, which is the Dirichlet energy of this map. With these ingredients now defined, we can introduce what the energy functional is. We fix some representation of gamma into G, and we consider the function that simply assigns to each complex structure the energy of the associated equivariant harmonic map. I now claim that this function descends to Teichmüller space. Namely, if you have some diffeomorphism of the surface that's isotopic to the identity, then and consider two complex structures which are equivalent, one being the pullback of the other, then by this essential uniqueness clause that we saw in the previous theorem, we see that the following relation must hold between the two harmonic maps. Here phi tilde is the lift of the diffeomorphism to the universal cover. Plugging this formula for the harmonic maps into the formula of the Dirichlet energy functional, we find that they are equal, which means that this function does indeed descend to a well-defined function on Teichmüller space. And we use this to define the following. The energy functional of a representation is the function on Teichmüller space that assigns to each equivalence class of complex structures the energy of the corresponding equivariant harmonic map. And this energy functional should be thought of as a measure of compatibility between the representation and points in Teichmüller space, meaning that a point in Teichmüller space is very compatible with the representation if the energy functional on that point happens to be low, meaning that this point in Teichmüller space, the Riemann surface that it determines, can be mapped equivariantly into the symmetric space with little stretching, with a low energy. So this is the definition of the energy functional. And now let's spend a little bit of time on answering the question why this energy functional is actually of interest. And my interest in studying it is that it can be used to study Hitchin representations. So let us first introduce what these are. And for this we take first a step back and consider the Teichmüller space, which before I've introduced as the space of complex structures on a surface. But we consider the following fact, namely that Teichmüller space can be realized as a connected component of a representation variety. We consider the representation variety of gamma into PSL2R, which is the set of all representations of gamma into PSL2R considered up to conjugation by elements in PSL2R. This is a topological space, and one of the connected components turns out to be in a one-to-one correspondence with Teichmüller space. Let's very briefly state how this is done. A representation which lies in this particular component is called a Fuchsian representation. It turns out that such representations are discrete and faithful, and what we then note is that PSL2R acts by isometries on the hyperbolic plane, and hence, given a Fuchsian representation, we can consider the quotient of the hyperbolic plane by the image of our representation. This yields a Riemann surface which has the same genus as our original surface S. Moreover, the choice of representation induces a identification between S and our new Riemann surface X. And this diffeomorphism is well defined up to isotopy. And now, using this identification, we pull back the complex structure on X to a complex structure on S, which determines a point in Teichmüller space. And this assignment from a representation, a Fuchsian representation, to a complex structure gives the identification between Teichmüller space and the connected component of this representation variety. And now let's move towards Hitchin representations. These are in a way a generalization of these Fuchsian representations. They were discovered by Hitchin. He discovered that the representation varieties of gamma into G, where G is a split real simple Lie group, these representation varieties contain similar components which consist entirely of nice representations, let's say. Let's first define what the Hitchin components are, and for this I will restrict myself to the case of G equals PSLNR, which makes the notation a little bit easier. And we use the following fact. There exists an irreducible representation of PSL2R into PSLNR, and this representation is unique up to conjugation. Then the Hitchin components can be defined as the unique component of the representation variety that contains all representations of the following form. Here we consider ρ a Fuchsian representation and we compose it with this irreducible embedding of PSLNR into PSL2R into PSLNR. So in other words, yes. And then any representation that's contained in such a component is called a Hitchin representation. And put differently, a Hitchin representation is any representation that can be continuously deformed into a representation of this form. And these Hitchin components and Hitchin representations have been studied a lot, generally under the umbrella of higher Teichmüller theory. I do not have time to explain perhaps too much why these components are so interesting, but let me mention that these Hitchin components share a lot of properties with Teichmüller space as we saw it in the previous slide. In particular, for example, all Hitchin representations are discrete and faithful, just like the Fuchsian representations were. And well, there are many more common properties, and these shared properties make the Hitchin components so interesting to study. Now the question is, how does the energy functional come into the study of the Hitchin representations? First, you need to know that the Hitchin components can be parameterized by means of Higgs bundles. And this parameterization is the way that Hitchin originally discovered the Hitchin components. And they allow you to study Hitchin components, which are just sets of representations, by means of these Higgs bundles, which are complex analytic objects, meaning that they are amenable to study using complex analytic tools. And this parameterization is very useful. However, it comes with a disadvantage. Namely, you need to know that the mapping class group acts on the Hitchin component. The mapping class group can be realized as the group of outer automorphisms of the fundamental group of our surface. And it acts on the Hitchin components simply by composition. Namely, an element in the Hitchin component is a representation of the fundamental group. An element in the mapping class group is an automorphism of the fundamental group. And by composing these, we obtain this action on the Hitchin component. And then the annoying thing is that the Hitchin parameterization, which is very useful to study these components, does not respect the action of the mapping class group. And this is a little bit sad, because it's very interesting to consider the quotient of the Hitchin components by the action of the mapping class group, similarly to how it's interesting to study the quotient of Teichmüller space by the mapping class group, which is the moduli space. However, because this parameterization does not in any way respect the action of the mapping class group, we cannot obtain any useful information from this parameterization about this quotient. And this is a situation that we would like to remedy somehow. And a program to perhaps do this was initiated by Laborie. He first considered the energy functional as a way to study Hitchin representations. And what he proved is that this functional as a function on Teichmüller space, when associated to a Hitchin representation, is actually proper. And that means in particular that each energy functional has a global minimum. And what he conjectured is the following, that this minimum is actually unique, or perhaps even more strongly, that the energy functional has a unique critical point. And this conjecture has been proven for simple Lie groups of rank 2, and it has recently been disproven for a particular Lie group, namely 3 copies of PSL2R. But other than these quite specific examples, we know nothing about whether the conjecture is true. But let me mention why it would be nice to have a confirmation of this conjecture. Suppose that it's true. What then happens is that you can do the following. You can find a mapping class group equivariant projection from the Hitchin components onto Teichmüller space. Namely, you pick a Hitchin representation, consider the associated energy functional, and then if Labourie's conjecture is true, it has a unique minimum on Teichmüller space. And you map your representation simply to this minimizing point in Teichmüller space. And because this construction is very natural, no choices have been made of any sort, this kind of is automatically mapping class group invariant. And then there's some more good news if Labourie's conjecture holds. Namely, using this mapping class group invariant projection, you can also construct a parameterization of the Hitchin component, which is also mapping class group invariant. The precise construction is, for example, detailed in the paper of Labourie where he formulates his conjecture. So, to summarize, the energy functional is an important tool in studying the Hitchin components because it could help us with constructing mapping class group equivariant parameterizations of the Hitchin component, which at the moment do not really exist. And as I said, for rank 2 simple Lie groups, we know the conjecture to be true, and for such Lie groups we can parameterize the Hitchin components nicely, but for other components we at the moment do not have any idea how to proceed. And in the rest of this talk, or the second part of this talk, I will discuss some results regarding the energy functional, and I hope that with this short overview of its place in the theory, you agree with me that it's an interesting thing to look at. And that's the end of the first part. Thank you.